So let me start. I want to come back to this proof that I kind of botched up last class. I don't want to do the technical details again, but there were some ideas that because I was flustered with the technical details, I sort of didn't bring out the ideas. And so let me just try to bring out what the idea was that I missed or that I didn't bring out on Friday or Thursday. So on Thursday we were so we had this proposition that said, suppose we want to rule out points of non-differentiability of our potential. And so we imagine we're at a potential point of non-differentiability where the potential looks like this. That's U. It's its own second transform. And we picked two nearby points. We had picked some x0 and x1 for which the corresponding y0 and y1 were relatively far apart. So it was like the change in x was small compared to the change in y. Was that it? I think that was it. Right. And then we looked at a supporting copy of B over here. So this would be like B of something, and another supporting copy of B over there. Again, this is B of something, I guess y0 minus lambda naught, and then this is B of something y1 minus lambda 1. It touches here. And so, and then the idea of the proof was we look on the line segment joining x0 to x1, and we find the point, I think I called it x2, where these two things cross, and we normalize this to happen at height 0. And then we rotate, as we slide yt between y0 and y1, there's a corresponding b that goes through here. Maybe I don't know, I draw it like so. But we bump it up to make it go through, we bump it up to here to make it just touch u at x2. And then we look on some ball of radius epsilon around x2 on the boundary of that ball. And the claim was that that this bumped up copy of B, so this was like B something y minus a constant depending on y. The claim was that we set the whole thing up. So the setup gives if x is at distance epsilon from x2, then b of, I guess, b of y minus lambda y is less at x, is less than u of x for all x in this boundary of the ball of radius epsilon around x2. And on the other hand, and this is for all y in the sausage around the middle third of this delta sausage around y 1/3, y 2/3, let's say. So somehow the technical bits that I struggled with were to get this inequality here, controlling all the errors to make sure that we have this inequality on the boundary of this ball. But on the other hand, whereas at x2, we have equality, because that's how much we've bumped it up here. We bumped it up exactly to have equality over this point. And so basically what that means is that therefore u of x minus bx y minus lambda y is bigger than 0 on the boundary of the ball. And it's equal to, it's equal to 0 if x equals x2. And so that means it has a local minimum somewhere in the ball. In the interior, since it's positive on the boundary. At some x, depending on y. And this construction, again, this works for every y over in this sausage. So if each of these y's here comes from some x in the interior of the ball, in the sense that this function has a local min. And what does that mean? That means basically that that if I differentiate with respect to x at this local min, I have 0 is du of x minus dxb at xy. If the x is a point of differentiability, and if not, what I have is that dxb of xy is still in the local subdifferential of u at x, the classical, not the b subdifferential, but the classical local subdifferential. And then what I need to conclude the argument is that the mapping G at x really should map to y. And for that to be true, what I really want is that xy actually belongs to the b subdifferential. So in other words, I found a low, I know that on this ball around here, the picture, one thing that's slightly misleading about my picture is that that you can go through this thing. It's just that it agrees at x. So that this thing, it's not like this thing is tangent to you at x2, but it's tangent to you in some, by dropping it down a little bit, it becomes tangent to you in some nearby point x, which is still in the ball of epsilon around x2. And then basically we had a lemma 2 classes ago that said that if you're a local supporting plane copy of B, then you're a global supporting copy of B. So you might worry that somewhere far away from this picture, that this black curve comes down and passes through the green curve again. And basically our local global result says this can't happen. But local B supports are global B supports. By A3. That was a corollary. Right? Because in other words, it's not enough to know that the point nearby, the X in this ball, maps into the sausage. We want that we don't want any part of the sausage coming from somewhere else. So we want to know that there's no X further away, which also comes from the sausage, because our whole argument is based on the fact that this sausage is too big to fit into this ball. And this local from global argument, which relies on this corollary that used hypothesis A3, tells us that, in fact, every point supplying a Y in this sausage is contained in the epsilon ball. Does that make sense? So it's not just that that there's some point in this ball that maps into the sausage, but in fact, every pre-image of each y in this sausage lies in the ball, and that's why we needed to deal with this. We needed this local to global argument there. Okay, so that's the part that I kind of I don't think I said much about this on Friday, and why did we go through the problem of the possibility of proving this corollary, or the hassle of proving this corollary, and so on, and where was A3 used? That's where A3 is used. To know it's only under condition A3 that local B supports are in general global B supports. All right, great. Questions about that? Okay, so what I thought, so let me make a couple of remarks. So by now I've managed to grade the assignments. The first assignments, they were fine. They were pretty good in general. There were a couple of people that it looks like haven't seen calculus of variations before. So those people had trouble with the first problem, the problem on showing the geodesic equation for Riemannian geodesic. I mean, I guess there are some subtle points that I could make about the assignment. So of course, question one, you needed to use calculus of variations. So the basic idea of calculus of variations, maybe I'll say it once, is, so we had the energy associated to a curve where X was a mapping from maybe the unit interval into some domain in R2 or Rn. And the basic idea is you want to, if X minimizes on some class of curves of fixed endpoints, so min subject to X of 0 equals X naught and X of 1 equals X1 among smooth curves, then what that means is that if I look at perturbations of X with any Y, I guess doing the same thing, except that I want Y0 and Y1 to both vanish, then if X is a minimum, so let me take X to be an argmin. Let's take, we'll call it X star. And then I perturb that, then the basic idea is that if this derivative exists and S equals 0 is a minimum, then the first derivative has to vanish. And so basically what you want to write this out as is, after an integration by parts and so on, this is going to be something like the variational derivative of E with respect. It's going to be some expression, which I'm just going to call the variational derivative of E with respect to X, but you don't need to know what that is. Integrated against Y. This depends on T. And this is supposed to hold for all smooth Y subject to these endpoints constraints. The endpoint constraints help you do an integration by parts. And so the conclusion is that whatever this expression is, which appears integrated against Y, it had better vanish if this integral is to vanish for every Y. So let's see, the second question had to do with the Banach-Alaoglu theorem and the Riesz representation theorem. Now, there are some choices about whether you apply duality on continuous functions with compact support, or continuous functions which are not a Banach space, or continuous functions that decay to 0 to infinity, which does form a Banach space under the supremum norm, but it turns out not to be essential for either of these theorems. The most common mistake that I found was that, so once you have a sequence of measures converging in some weak, let's say weak star, or narrow, or sometimes this is called the wide topology, to a limit, a lot of people, when they wanted to check that the marginals were preserved under limits, they wanted to apply, they said, well, let's let U be a subset of whatever space we're in, and then apply to characteristic function of U. And they wanted to argue something like that this limit would be So what's the problem with this argument?
Characteristic functions aren't continuous.
Exactly. So characteristic functions aren't continuous, and so you don't have this. So this, whatever notion of convergence, this is convergence against continuous test functions. And at best, if you might, if for example, if you might have an inequality like if U was an open set. So if U was open and you had a sequence of measures, of course, the measures, like you could have a sequence of Dirac masses which march to a boundary point. They're going to converge weak star to a Dirac mass at that boundary point, but the boundary point is going to be outside the set. And so if U is open, then you might get an inequality like this. And you might get the reverse inequality if U was compact. Maybe things are, I don't know. Yeah, you can probably get the reverse inequality if U is compact. But so you need to argue a little bit more. So either you need to, so you can't apply this directly. You would have to do both open and compact sets and use, or you'd have to do some smooth approximation to U, like basically using something like Urizone's lemma. Or you could just say, you could take your definition of what it means for gamma to have marginals mu plus and mu minus. Instead of saying, one definition is that you have this agreement, but this is the definition that you really need to have, and vice versa for the other side. This is the definition that you would want to use characteristic functions for. Another definition that you could use is that the integral of the gamma of a function depending of a continuous function depending only on x is the integral of f against mu. And then there's this question of, do I insist that it be compactly supported or go to 0 at infinity or just be bounded? But in any case, f would be continuous. And similarly on the other side, gy d gamma xy should be integral gd mu minus. But otherwise, if you really want to do this with sets, what you need to do is you need to take an arbitrary Borel set, what should we call it, C, and approximate it from inside by a compact set and from outside by an open set, such that the whatever measure you're trying to, gamma of the open set minus the compact set is less than some error tolerance. And then you can use these arguments, or then you can find a Urizone's lemma. Somebody's lemma tells you can find a function which is, let's call it phi, which is 1 if x is in the compact set, and 0 if x is outside the open set, and between 0 and 1 otherwise continuous. So you need to do an estimation argument like this and use Urizone. The way you prove that these conditions are equivalent to these conditions is by doing interior approximation by closed or compact and exterior approximation by open sets, and using Urizone's lemma to convert that to a continuous function which approximates this discontinuous guy. And the third problem was the one about the Krein-Millman theorem and extreme points of convex functions. So everybody, when I asked you to state a theorem, everyone looked up the theorem on Wikipedia or somewhere. So all the statements were essentially correct, modulo tiny misstatements maybe in some cases. But so Krein-Millman says that a compact convex subset K of a locally convex topological vector space is given as the closed convex hull of its extreme points. So let's say it's the convex hull of the extreme points of K, but then you have to close it in this, whatever the locally convex topology is. So TVS is my abbreviation for topological vector space. And of course, when I ask you to state these theorems, I don't just want you to go look them up on Wikipedia. I want, if you haven't thought about, if you never thought about these theorems before, I want you to kind of try to figure out what the definitions are that are being referred to and what the context is, and try to come to some understanding of the theorem. But so what does it mean to be a locally convex topological vector space? Well, of course, every Banach space is locally convex and every Hilbert space is locally convex, but sometimes you have topologies that don't come from a norm. And then what it basically means is that the topology is generated by convex neighborhood, you have a convex neighborhood base. So for the various weak topologies that or the narrow, whatever, weak star, those kinds of topologies come from these convex neighborhood bases because they're generated by linear functions, basically. So they come from half space neighborhood bases or sub bases. And when you intersect half spaces, you get something convex. So the biggest mistake that people made with this was they said, so when you got to, I don't remember this 3B or 3C, and you want to show that there exists an extreme point in the set gamma mu nu, such that which was also maybe a minimizer for, so let's call gamma star, argmin gamma integral cos d gamma, let's say, for some linear, continuous function C, bounded continuous function C. They said, well, so they said every gamma in gamma is a convex combination of extreme points. So what's wrong with this? I mean, often they said gamma can be written as 1 minus t gamma naught plus t gamma 1 with gamma naught and gamma 1 extreme. That's clearly not true, but if they were slightly better, they said, well, you can write it as ti gamma I counting up to some k, where the ti's are positive and sum to 1, and the gamma I is extreme. What's wrong with this?
You have to close the convex hull first. So it's
exactly
by
so this would be true if I didn't have the closure here. But what's rather true is that you can find these convex combinations of extreme points such that, but you need to find a whole family of them. So let's say k of n, t of n, and gamma of n, such that as n goes to infinity, this converges to gamma. In the topological vector space. And so that spoiled some people's arguments. And the other common mistake was to show that if you looked at the set of minimizers, so a correct argument is that argmin of gamma is compact and convex. So at least one point, let me call this set A. So at least one point in A is extremal in A, but that doesn't necessarily mean it's extremal in gamma. Or you still need to make an argument that it's not enough to be extremal in A. You also need the point to be extremal in gamma. That was the other common mistake that I saw. Not that common, but a couple of people made it. Other questions about that? Okay. And it's funny about this business about closing the set. So one of the reasons that it's misleading is I think that if the topological vector space is Euclidean space, so in other words, if it's finite dimensional, then I think that you don't need to close it. I think that I think that it may be true that then there's a simpler version of Krein-Millman that says K is actually the convex hull of its extreme points, but in infinite dimensions, this isn't true anymore. You really need this closure. Okay, so I'm going to change gears a little bit, and I want to come back to duality, and I want to come to thinking about the case where the transportation costs were. So I want to think about the case m plus equals m minus. I'm probably going to call this m, although some authors would call it x. And some authors would reserve m for manifolds, and they'd use x for metric spaces, which are not manifolds. I'm a little hesitant. I could use capital X, I suppose. I'm a little hesitant to use straight up X, because then my points lowercase x and my capital X may get confused with each other. But certainly there's a literature which makes this distinction. I want to come back to thinking about the case where the cost is either the distance or the Pth power of the distance, and thinking about using the transportation cost to define, so transportation lifts d from m to the set of probability measures on m, to define a metric on the set of probability measures, and then understanding. I mean, basically what I'd like to show is that if M is a polar space, then PM is a polar space. And moreover, I want to understand what topologies these metrics that I'm going to use this total transportation cost give on PM, and what kind of geometry. And I guess it's nice to point out that we've already seen, before I go further, we already saw in Thursday's lecture, how somehow we saw the Riemann tensor popping up. And the Riemann tensor was somehow related to these kind of multiple point inequalities involving CXY. And so of course, the Riemann tensor popped up because CXY was on a manifold. But you can imagine trying to make sense of conditions like A3 in a setting where you don't have a manifold. And so if A3 is really a curvature condition on some associated metric, if you had less smoothness, you can imagine capturing that curvature condition through conditions like A3 instead of through conditions on tensors, depending on the metric. And so that's somehow the next direction that I would go, but I have to develop this geometry of probability a little measure spaces a little bit to do so. And so the first thing I want to talk about is that, of course, we have this general duality theory that says the minimum of a cost against gamma when I minimize over all measures with joint marginals is the maximum of functions of integral u d mu plus v d nu, where I guess my sign convention here is that c is going to be bigger than u of x plus v of y. Right, I've somehow, this is c is minus b, and when we wrote down the duality for b, the min and the whole thing was multiplied by -1, including u and v have been multiplied by -1. But we have this relation, and but the claim is that this simplifies. So Kantorovic's observation, if you read his 1942 paper, he doesn't have, this is not the dual problem he writes down. He writes down a slightly different dual problem, and it turns out that the dual problem he writes is only appropriate when the cost actually satisfies the triangle inequality. And then the claim is that you can rewrite this in the form supremum of integral u d mu minus integral u d mu minus. And where the constraint on u is now that the Lipschitz constant of u is less than 1. And so the first thing on my agenda today is to show that when C satisfies the triangle inequality, you have the simpler form of duality, which only involves one function u instead of two functions u and v. And I think I mentioned this once before, but a funny thing about Kantorovic's paper is that this is the duality he claims to prove, even though his proof basically has a gap. It has a gap, it can be filled, but it's it's not really correct the way it was written. And he doesn't actually assume that C satisfies the triangle inequality, because at the end of the paper, he says, this works for general costs, but of course, the most interesting costs are the ones that satisfy the triangle inequality. So I think it's a little bit funny that this paper that he got famous for has these two, a mistake in the proof and a mistake in the statement. But on the other hand, it was one of these 4-page or 3-page papers published in the Compte Rendu Duality of the Academy of the former Soviet Union. And so I think contributions there were limited to 4 pages. And so they had a real premium on summarizing what the ideas were and not including all the details. And so on the one hand, this part of the Russian literature is kind of a joy to read, because things are short and succinct, and all the ideas are exposed and the details are suppressed. And on the other hand, occasionally it led to error. So these errors turned out to be correctable. Well, not the statement, but the one in the proof was correctable. But the statement could be rectified by writing it in this way instead of this way. And but sometimes the Russian literature's crept into the Russian error. Errors crept into the Russian literature that then were had to be fixed. Were a lot of trouble for other people to fix later. People used the results without realizing that they weren't quite right as stated. Okay. So yeah, I want to show this simplification, and the basic lemma is that which implies this is that when C is D, then U, now it's a mess of signs, but so minus U is its own second transform under minus C. If and only if, let me write it a bit better. U B B tilde is minus U, where B is minus C. If and only if the Lipschitz constant of U is less than 1. So that's somehow the first observation. And then the second observation is that I can take V up here to be minus U. So let me try to prove the lemma. So well, so the first observation is that how should I write it? I should write it for every Y, if I fix Y, then I have a 1 Lipschitz function. Because so let me give this 1 Lipschitz function a name. I guess I could call it L of X, Ly of X or something. And so the basic idea is, if I wanted to look at Ly of X1 minus Ly of X2, that would be, since C is D, that would be D of X1Y minus D of X2Y. And this is less than X1, X2 by the triangle inequality. And since I can change, and the constant is 1 here. So I can change, since X1 and X2 are arbitrary, I also have Ly of X2 minus Ly of X1 is also less than dx1 x2 by the same argument. And that shows that L is 1 Lipschitz. So the cost is 1 Lipschitz as a function of its first argument. By symmetry, it's also 1 Lipschitz as a function of its second argument. And so if minus U transformed twice is minus U, then in particular minus U of X is sup over Y of minus D XY minus minus ub, I guess, or maybe minus negative ub. And so the point is that for each y, these are all one Lipschitz functions of x. And we saw a while ago that when you take a supremum of functions whose Lipschitz constant is 1, the supremum is also has Lipschitz constant 1. So that's one direction. If I'm B convex, then my Lipschitz constant is less than or equal to 1. And conversely, if lip u is less than 1, we claim u is its own second transform. And so let me see how am I going to show this. So what does Lipschitz constant of u less than 1 it mean? So Lipschitz constant of u less than 1 says that ux minus ux1 minus ux2 is always less than dx1 x2 and also bigger than minus d x1 x2. So I'll have u of x1 is bigger than the sup of minus d x1 x2 plus ux2. And, or I could write this as minus minus, maybe that's better. So this is minus u to the minus u to the b. So what so far I've shown that u is bigger than minus u to the b. And I guess if I b transform again, maybe I need to multiply by minus 1. The minus signs get confusing, don't they? So u is bigger than minus u to the b, so minus u is less than minus u to the b. And if I b transform that, I will get, since b transforming inverts the signs, I'll get the b transform of minus u is bigger than give me a minute. So somehow, let's see, if I multiply by minus again, I think I'm not improving the situation with all these minuses, but So what we always have is that minus u, when you twice transform it, is less than minus u. Now we want to see that it's bigger than minus u as well. Does anyone see a way out for me? Maybe I should, I think it's really simple. Let me just see if I So I've tied a knot around myself. So let me basically, let me have a quick look in Sant'Ambrogio and see what he says. So Sant'Ambrogio says, suppose that the Lipschitz constant of u is less than 1. And he says that the claim is then that, so I get away from the minus signs, that claim is then that u is actually the infimum over y of the cost, which is d, minus u, which is plus u. This is the direction I want to show. And one direction is clear because I can always take, this infimum is always less than what happens when I take y equals 0. And when I take y equals, or when I take y equals x rather, sorry, I messed this up. This should be a y. That looks better. When I take y equals x, the distance is 0. And so that's less than u of x. And I haven't used the Lipschitz 1 condition yet, but the Lipschitz 1 condition says, so this is a question mark here, right? So we've just shown this infimum is on the one hand less than u of x, and on the other hand, we know it's bigger than u of x because if I remove the infimum for a second, this would be just an expression of the Lipschitz 1 condition that u of x minus u of y is less than d. And so that holds for all y, and so I can put the infimum in. Great. Sorry, so I didn't need to tangle myself up so much here. So I'm going to get rid of that. Questions? So there's this kind of surprising, but again, the thing to notice is that this is inf of minus u. And so that, that the uv, so when I now want to minimize maximize u d mu plus v d mu minus over u plus v less than d, what this calculation is. So we had a general result that said we can always find a pair of minimizers, u and v, and now the signs are all going to be messed up, but we can always find a pair of minimizers minus u and minus v, which agree with their own second transforms under v. So this would be rather minus v transform, and this would be minus u b transform, since the d is symmetric, so there's no difference between the b and the b tilde transform. And what the calculation that I just went through is showing is that really this means that minus u is v and minus v is u, because this u here can be replaced by minus u. And so this becomes the soup over integral u d mu plus minus u d mu minus. And we said that the condition was, instead of u being its own second transform, the condition was Lipschitz, u is less than 1. Okay, great. Questions? And it's easy, it's relevant since the set of functions whose Lipschitz constant is less than 1 are already equicontinuous. It's easy to show existence. I mean, we had an existence proof independently, but it's easy to show the max is attained, even easier than in the general case. And even on spaces that are, I mean, even if the space is not compact. So this is a very useful characterization when one wants to come to thinking about topologies. So here's the claim. If I take two measures on the same metric space, and then I want to define the p distance between those two measures to be, I guess, the Kantorovich minimum, the minimum of the integral of the pth power of the distance d gamma, overall gamma having the correct marginals, and then you have to take the pth roots. And the claim is that gives a metric. On the space of probability measures. Well, okay, so now there's a little bit of a, so this would be true if M is compact and it gives a metric on a certain subset, which depends on P otherwise, where what is the set of good measures? It's the set of measures which have the additional property that they have so-called pth moments. So the integral of dp x naught d mu should be finite. For some x naught. And it doesn't, this definition looks like it depends on x naught, but it doesn't really depend on x naught because if it's true for some x naught, it's true for all x naught, essentially as a consequence of the triangle inequality. So let's say measures with finite pth moments. And so I claim that this is a metric, which means, so what do I need to check for this to be a metric? What are the usual properties that a metric enjoys? So someone put it in the chat.
Joaquin already has it in the chat.
Okay, great. Right, it should be symmetric. And so in other words, dp should be d mu minus mu plus. And that's pretty clear because this whole definition is symmetric. And it should be the case that, so i.e. Symmetric. It's also clear it's non-negative because this is non-negative. Non-negative. Which is, so these two are obvious. We want d mu plus mu minus equals 0 if and only if mu plus equals mu minus. So it should vanish only on the diagonal. And that's not hard to check, and maybe we'll check it in a minute. And then we want the triangle inequality. And the triangle inequality is actually the only non-trivial thing here. So let me take care of this one. Well, so if 0 is d of, that implies there's a joint measure gamma. Having mu plus and mu minus as marginals. And so how can anyone see how to finish the argument from here?
So in the definition, like you know that this gamma, you know the dp of mu plus and mu minus is equal to 0, and so we've defined it as this integral, and so you know that in particular it's the integral of something that's non-negative, and so you know that the integrand has to be 0 almost everywhere.
Right. Yep. Yeah. So can anyone finish the argument from there?
So then that means gamma just has to live on the diagonal.
Yep, that's right. Gamma of m squared minus delta is 0, where delta is the set of points xx. But the diagonal is the graph of the identity map. And so we had a theorem that said whenever you have a measure that's supported that vanishes outside the graph of a map, then gamma will actually be the push forward of its left marginal mu plus under the identity cross that map. And if I compose this with projection onto the second coordinate, so let's say projection 2 or projection m minus of gamma, which is mu minus, it says that mu minus is the identity push forward mu plus. But the identity map push forward mu plus is mu plus, so there mu plus is mu minus. Okay, so everything was straightforward except the triangle inequality. And so to show the triangle inequality, I'm just going to just think about compact spaces so I don't have to worry about there's no problem with the existence of minimizing gamma and so on, which otherwise I would need to use this finite moment condition to deduce. So to show the triangle inequality, the situation is basically the following. Right, so the triangle inequality asks that d mu plus, d mu minus should be less than d mu plus omega plus d mu minus, or d omega mu minus for every omega in the right space, in the relevant space. And so the right-hand side here, so if I think, yeah, sorry, this is dp. The right-hand side, this is going to be equal to dxy to the pth power d gamma, let's call it gamma 1 or gamma 1 2 of xy, and then the pth root plus dyz to the pth power, let's say d gamma 2 3 of yz, and the pth root. And so the idea where gamma 1 2 and gamma 2 3 are the optimizers in the definitions of these two distances here. And so then the idea would be, I would like to construct from, so I need to combine gamma 1, 2 and gamma 2, 3 to construct a competitor. I don't know what to call it. With marginals mu plus and mu minus, such that then, of course, maybe I'll put a tilde on it, such that the true distance between mu plus and mu minus maybe is not equal to what I get from this gamma tilde, but it should be bounded above. Well, it's always bound. Whenever you have anything in here, you get an upper bound. This should be xz, I guess. And sorry, this should be gamma 1, 3. And hopefully I'd like to construct gamma 1, 3 in such a way that I know, so that I know this is the key inequality that I should have, that this is less than this sum over here. That's the idea. And to do that, I need to glue gamma. I mean, what I want to do is kind of glue this guy together with that guy. And so i.e. need a gamma tilde, which is now going to be a probability measure on the product of the three spaces, such that I know what the first projection is. So I want the projection onto the first two marginals to be gamma 1, 2, and the projection onto the last two marginals to be gamma 2, 3. And if I can find a gamma tilde that has this projection onto the first two and that projection onto the last two, then I take its projection onto the first and the last, I'll get the gamma tilde 1, 3 that I want. Does that make sense? And then the question is, does such a thing exist? Well, okay, let me defer the question of does it exist for a moment. And if so, then let me finish the proof. Then this quantity here, so I can switch back to black, I guess. This integral of dxz p d gamma tilde 1, 3. If gamma tilde 1, 3 is the projection of gamma tilde onto the first and third coordinates, then gamma 1, 3 is the projection onto the first and third coordinates of gamma tilde, then I can also write this as integral dxz p d gamma tilde xyz. That doesn't hurt at all. And I can also, by the triangle inequality, this is of course less than dxy plus dyz. And I'm really interested in the pth root of this after all. And you might recognize this as, well, does anyone recognize what that is? That quantity there? So you might recognize this as the LP norm with respect to gamma tilde of some function. Right, and the function is the function dxy plus dxz, or yz rather. And then because the LP norm is a norm, I guess this is maybe, I'm not sure, is this Minkowski's inequality? And then we find that then the right-hand side here is exactly equal to this sum of these two terms here. it's gamma tilde x, y, z, but the integrand only depends on x and y. So it's also gamma tilde 1, 2 of x, y, pth root. Something similar happens in the other term. It would be gamma tilde of x, y, z, but the integrand only depends on y and z. So it becomes gamma tilde 2, 3 of y, z, pth root. And so this whole story gets reduced to this question that I wrote in red, which is if I have a marginal on the first two factors and a marginal on the third two factors, with the compatibility condition that when I project them onto the middle factor, the projection onto the middle of gamma 1, 2 agrees with the projection onto the middle of gamma 1, 3, gamma 2, 3 rather, which is basically we call it omega. So if I have a marginal on the first two factors and a marginal on the last two factors, which are consistent in the sense that they both project to omega, can I find a triple measure on the triple space having its first two its marginal projection onto the first two this thing and its projection onto the last two that thing? That's the question. Is it clear what the question is? Does anyone know what the answer is? So the answer is a little bit involved. And so the answer is going to take us into a digression. So in Villani's first book, he calls this the gluing lemma. I mean, of course, the answer is going to be yes. But that such a thing exists. But the nice way to show it is by using a technique called disintegration of measures, which, or it's also in the probability world, it's also known as the existence of conditional probabilities. And that's a very convenient way for us to do this gluing that we want, the gluing of gamma 1, 2 to gamma 2, 3 under this consistency condition, that when you project them both onto the y variable, you see omega. So this is a, and I put a link to an article on the homepage that gives I think a self-contained proof of the disintegration of measures. And let me not, before I state the theorem, let me try to give some intuition. So for example, in situations like where you have the unit square, you might have area measure on it. And if you have some subset of the unit square, call it E or whatever, so I take a nice measurable Borel, whatever you like, E, and you would like to factor the area and say, well, if I looked at the length of every vertical segment in E, and I add up these lengths in the way, that should give me the area of E. And in fact, this situation is so simple that we know that this is in fact true. The area of E can be written as the integral from 0 to 1 dx, the length of E intersect the set x cross 0, 1. And so this happened to be a very nice situation because we knew a priori that the area was actually equal to length, the product measure of length with length in the x direction with length in the y direction. But it won't always be the case. So if we might want to decompose the unit square into some other kind of some other segments. And then we might want to look at our set E, and we might want to be able to relate the area of E to it turns out that if the segments are not parallel to each other, it's hard to relate the area of E to the intersection of the lengths, and you can it won't just be the lengths anymore, and you can kind of see this if you think about polar coordinates. So if I went to polar coordinates and I took some set E, the area of E is not necessarily you can imagine that it's something like integral d theta from 0 to 2 pi, but it's not the length of the intersection with theta anymore. It's something else. It's because the conditional probabilities for a given theta here, the measure is not dr. It's sort of dx dy is r d theta dr. And so for each theta, the conditional probability is not just the length in the r variable, it's some kind of weighted length, where the length gets weighted by how close you are to the origin. And this theory of disintegration of measure tells you if you have a probability measure on some space, and you want to disintegrate it into fibers that might relate to each other in a complicated way, how can you write the total measure of E as some kind of integration over a measure on fibers cross a measure on each individual fiber? So somehow I'd like to decompose the measure on the whole space in a sort of semi-direct way. I'd like to put measures on each of the fibers, and the measures on the fibers may vary from fiber to fiber. And then I'd like to have another measure, which is on the space of fibers, so that I can get the total area by composing these things. And if this was a discrete world, if I was doing discrete probability, then things would be very simple, because you would have some, like, the probability of some event U can be written as something like a sum over possible outcomes Y of the probability of U given Y times, or let's say I had a random variable, capital Y equals Y, times the probability of capital Y equaling Y. So that somehow, if I wanted to partition E into a finite number of sets, then it's pretty clear. Then I could get the total measure of E just by adding up the measure in each of the three sets. And it's clear that I would just restrict area to each of these three sets. And somehow that's what this formula is telling me. Now I want to do it for an uncountable number of things. And it's not quite as straightforward anymore. And that's what this theorem allows me to do. And so the theorem goes the following way. So suppose M plus D plus is a Polish space. And the same, both of these are Polish. So I suppose I have two Polish spaces. And in fact, radon would be enough. So we talked once before that Polish spaces have the property that every probability measure is irregular, in the sense that you can approximate the measure of any Borel set by compact sets from inside. Radon spaces are defined by that property. So a space is radon if every probability measure on the space can be inner approximated by compact sets. So it's sort of saying compact sets are dense in the space in some sense, or measure theoretically dense. So if I have two Polish or radon spaces, and then I'm given, it sounds like transport already, given a probability measure, a Borel probability measure on the first space, and a map, I don't know what to call it, let's call it Q, from the first space into the second space, Borel. Q is going to play the role of my capital Y up here. It says there exists essentially unique set of measures mu plus Y, conditional measures for Y and M minus, such that such that several things happen. So point one is that, and I'm going to define the measure on the target space to be Q push forward the measure on the source space. mu minus almost every y satisfies mu plus y of q inverse y equals 1. Sorry, these are probability measures on the first space. So the idea here is that I'm going to decompose mu plus into these pieces which are supported on these sets. So let me draw the picture again. So the picture was like this. These fibers would be the level sets of Q. And so, so I'm going to have for each image point Y, I could look at the pre-image, which would be one of these fibers. I'm going to have a measure on each of those fibers, which vanishes outside it. Secondly, there needs to be some measurability. So I think the mapping for every Borel set, the map y in M minus to mu plus y of B is mu minus measurable. And then the final condition is that I guess it doesn't matter whether f is continuous or whatever for every Borel f on M plus. If I want to know the integral over M plus of f, I can get it by integrating f d mu plus y of x, and then over, I guess they vanish outside this set here, so over q inverse of y, and then integrating over all y. So this formula here is telling me, yes, I've decomposed mu plus as an average of all these conditional measures averaged with respect to mu minus. And this formula here that I just drew the box around is supposed to be analogous to this formula here from the discrete setting. So I decompose the probability into a bunch of conditional probabilities averaged over the probability of the condition. So these would be like the conditional probabilities, and this is the probability of the condition. Is it clear what the content of the theorem is, or what the statement is? Yeah, okay. Maybe I have a quick show of hands. How many people have never seen this guy before? Great. So how many people have seen it before? And I can just, so I can say, what are the ideas of the proof? So, and it's good, otherwise you can consult the article that I posted, which is by Chang and Pollard. But the ideas of the proof are actually not that bad. To put it together in a technical way is a bit challenging, but the idea of the proof is, I made some notes about this. Right. So the idea is to look at Q push forward f d mu plus, where f is arbitrary. And of course, this is going to be a measure on M minus, because that's where Q maps into M minus. And so I can look at its Radon-Nikodym derivative with respect to mu minus. Nikodym. This measure, dq push forward f d mu plus, can be expressed as some G depending on F, d mu minus Y. And now the left-hand side is linear in F. And so that tells you that G of F should be linear in F as well for every Y. And in fact, the target space is Polish, so it'd be it'd be enough to look at countably many Y. If I know the value of, well, okay, probably. Let me not try to say anything technical because I'll get it wrong. So anyhow, so it's linear in Y, and so then it's the Riesz theorem. The Riesz representation theorem says that basically, at least for mu almost every Y, gf of Y can be written as the integral of F against some measure. So there exists mu plus Y such that gf of Y is the integral m plus d mu plus. So that's basically where these conditional measures come from, is a judicious application of the Riesz representation theorem. And then once you have them, you have to go check that they satisfy the three criteria that we wanted. So it really is supported on the preimage under Q of that Y. It has the right measurability properties, and when I integrate an arbitrary function against a test function against mu plus, I can get the value of that test function by integrating against mu plus Y and then averaging it over mu minus. And of course, this simplifies a little bit if I take F to be a characteristic function of the set. Then it would say something like mu plus of E can be written as mu plus Y of E integrated with respect to mu minus. And that's very much of the flavor of what I started out saying, which is that I want to be able to decompose E into its restriction to these fibers. That's the fact that I'm restricting to fibers comes from step one in the proof. And I want to have some measure on each fiber, mu plus indexed by Y, such that when I average those guys over fibers using mu minus, I recover the total probability of E. Okay, and so now so the final situation is, let me come back to my question, which was given gamma 1, 2 in gamma mu plus omega and gamma 2, 3 in gamma omega mu minus, does there exist gamma tilde in the triple space such that gamma 1, 2 is the projection onto 1, 2 of gamma tilde, and gamma 2, 3 is the projection onto 2, 3 of gamma tilde? That was my question. And so the answer is yes, by gluing. So let's see how we do it. Let disintegrate so M is a Polish space, so in particular radon in all three cases. So disintegrate gamma 1, 2 using Q of xy equals y, let's say Q1, to get gamma 1, 2 of E is integral. Now the image, of course, Q1, maybe I should call this, let's Q1 push forward gamma 1, 2 is omega. So this is going to be an integral over M with respect to omega. And then I'll have gamma 1, 2, let's put the Y up instead of down, of E. And similarly disintegrate gamma 2, 3 using Q2 of YZ equals Y, because again, Q2 push forward gamma 2, 3 is omega, to get, so this is for all Borelli. Gamma 2, 3 of E would be the integral over m d omega, again, gamma 2, 3 y of E. And then I want to define gamma tilde. So I'm gonna write something formal again, first of all. Basically, I want it to be something like gamma 1, 2 y, gamma 2, 3 y d omega, something like that. I.e., and what do I really mean? I really mean that if I integrate an arbitrary smooth, whatever, continuous test function against gamma tilde, as long as I can define this, as long as I have a linear action, then I know gamma tilde if I know its integral against any continuous test function. And how do I do that? I'm going to write it as an integral over m d omega y, and then an integral over m squared x omega 1, 2 of y was xy, and then another integral over m squared d omega 2, 3 y of z. Right, so great. So so I define it by this funny triple integral, and now the observation is that if f of xy is f of xyz depends only on the first two variables, then there's no z dependence here. I can do this is yz. Let's see, do I have it right? It should be simple if I have it right. Oh yeah, sorry, wait a second. Maybe I didn't do the disintegration quite right. Okay, let me see. I feel like I'm out of time and I feel like I should clean this up. I should take the time to clean this up, maybe at the beginning of next class, to just finish this proof that, that once I've done these disintegrations, I can build the measure that I want. Right, so the so I have this observation in my notes. I say notice that, so if I have a mapping pi y, x, y, z, which picks off the y coordinate, then pi y inverse of y is basically the first factor across the last factor. So when I disintegrate these things, yeah, somehow I want to. So what's annoying here is that I have this y dependence hanging around, because if I didn't have that y dependence, when f was independent of z, I could just do the z integral, and it's a probability measure for each y, and so it would go away, and then I would have so somehow this term and this term would go away, and I'd be left with the fxy here, and but maybe that's not the point. Maybe the point is let f be a function of x only. Well, it's clearly that works, that I get mu plus is my left marginal. If f is a function of z only, I'm going to get mu minus is my right marginal. But okay, I'm sort of out of time, so let me try to clean the rest of this proof up next class, and I'll just wind it up there. Are there any questions before I turn the recording off? Okay, let me turn the recording off, and we can